will start in a minute there. All right. Well, let's go ahead. I want to do one real quick thing, and then I'm going to work a problem. And one of the quick things is to talk about, I know I've already talked about dot products, but I want to spin through what he's got and relate it to kind of what I should have erased all this stuff. Okay, all right. I had a purple marker. There it is. All right. So, okay, actually, I think I'm at the end of the dot product, so I think I need to go back up. So I know I've talked about dot products before. I want to kind of fill in any sort of gap that I left, because actually dot products are way more important than a lot of people think. And I will say that, okay, I don't think it was in this class. A couple periods, I set up the stream and I forgot to look. So if you look down here, maybe you could help me. If you ever see this black dot without a red dot on it, let me know, because I forgot to hit the start in fluids and they didn't get a stream. So they're like, where's the thing? Luckily, okay, if that happens, and it can happen, if you go into this area, you know, I will try to categorize these better, but I think I just clicked it. Did I not click it? There you go. These are tons and tons of problems. You can already see, I mean, there's a law of cosines and stuff like that. So I have a set of videos out there already made. If in fact I goof up and I don't click the stream, I'll try to replace it and say, go look at these two, this is what I did. Luckily in fluids, you know, if you think about it, 3 class periods times an hour is 3 hours, and then 15 weeks, which actually kind of boils down, you'll see that it's more like 10, because it's not a full hour. You got 30 hours of lectures. It turns out in fluids, I've got something like 60 hours, so I've got more content online than you would if you're sitting here. And it's the same content. The difference is you have to wait in between the pauses, I said. If you look at it on YouTube, you can push the speed up button, and you can, you know, I talk slow enough so double speed sounds like a normal human. So if it just so happens I do that, don't freak out, but just let me know, and I'll find the content. Okay, so apparently I thought I was at the introduction of the dot product, but I'm at the end of the dot product. So the dot, okay, so I just want to, this is kind of a review. Now, 2 things he does, and when you read this, the dark indicates the vector. This indicates the length of that vector. So if you go read a math book, the math book will say this, And they're really meticulous about, and that's the one thing I think that the engineering books fail to do. They fail to, and not all books, some are very much, they tie you to that. But this isn't one failure I see here. You have to read the text, but a mathematician just looks at this and says and sees that. So you don't need much words to write to recognize that's the magnitude of that vector and that's the magnitude of this vector. These two, this notation is annoying to me. But that's the case. This is the length of that vector, this is the length of that vector, that is a vector, that is a vector. That's of course cosine. So what he's saying is that's kind of the definition. But how does he get that? The mathematician will use the word projection. Is anybody going to take linear algebra? That is an available course for a math elective or a technical elective. I do not remember which one, so don't quote me. If you get more into math, you'll see this word over and over and over. And it comes in many different contexts. There's functional projections. And what you find out is for functional projections, they are heavily dependent upon the dot product here. And so a projection, you could just think of it as putting yourself a projector, putting a bulb in here. It shoots a light out. You have a vector right here. It projects it onto a face. So this is of length 5. I'm just making that up. How about I just make it a length A? So it's a vector A, and you want to project it out this way. Let's say that's the x direction. So if you're going to do that, you already know that. You take the magnitude of A, and you take the cosine, and that is this length. You were taught that in trig or pre-cal. I don't know. When I was there, they had a course that was called trig, and then it was calculus. So I don't know, why they've changed names. Probably just teach the same material. But that's something you already know. Now they're saying, I have a vector like this. We're going to project it. So we're going to get the same equation that we would through the projection. It just so happens that what we want to do is we want this B vector to be the I vector. By nature, that's length 1, and you dot those. What do you get? If you take A and you list it like this, A, X, I, plus A, Y, J, and yeah, let's go ahead and say Z, K, and you dot that with I, and use this relationship where you replace I dot J, length 1, 1, cosine of the angle between I and J is 90 degrees. Meaning J dot I, 0. K dot I, 0. I dot I, if I replace that, the angle between I and itself is 0, which means the cosine of 0 tells you it's 1. So, in fact, this becomes AX. AXI dot I, AYJ dot I, 0, AZK dot I, 0. So you get back that. That is actually what this is. So the x component of a vector that lays in this plane, projected onto the ground through sunlight or a projector, and just think of it that way. They'll use this term in math. That's what they're talking about, projecting it onto another plane or something. In this case, onto the ground. That you already knew from trig. Now this, you can say, I projected it. What did you do? You did the same thing, but you did it in a slightly different way. So with that in mind, you can do something else, and we talked about this before. I can take the projector and project it onto the wall. And guess what? now this is alpha, so the cosine of that times the length of that projects it onto the wall. So you can see AY is equal to A times the cosine of the angle of the projection, the angle between the vector itself and where you're projecting it onto. Okay, so that's why, in my mind, he should have introduced this before he introduced that part back there, which is why I took that material back up into there. So now what else can we do with this? So there's some extra parts. We roll through these. You've seen these before. So here he's got his, okay, now that we've got that kind of in our brains, so here's an A and a B, okay, there you go. So let's say we knew the length of A, we knew the length of B, we might want to find that. We might want to find, okay, I've erased it already, sorry. A, hang on, I can stick it way over here and it won't move away. A dot B is equal to the magnitude of A, magnitude of B, cosine of the angle between. In math they would write AB. In math they would say the angle between vector A and B, this vector and that vector. So maybe you know this. Maybe you know this as being, 4I plus 2J. And maybe you know this as being 6I. And you want to find this angle. What you do is you find this magnitude, put it right there. You take this magnitude, put it right here, and you take this and dot with this, and then the only thing you don't have is that, and you can find that. Now, there'll be problems that are related to that. Now he goes off and he does this law of operations. There are things called commutative. They have a lot of laws there. I'm working on a paper that has something to do with subadditive. So in other words, a function has nothing to do with these, but b less than or equal to the function of a plus the function of b. That's a subadditive. So the reason that's beneficial in what I'm doing has to do with risk, and the fact that if you don't have a subadditive, if your risk measure, whatever that risk measure is not subadditive, it can't be used in a functional sense. So there are a lot of risk equations that are out there, metrics, as you may say. But here's a commutative law, a scalar, and then distributive. You can do this and this and this, and they all obey that. So for a dot product, there's other things too. So here's what he was talking about before. If I take two vectors and dot them, that's 1, that's 0, that's 0, 0, 0, 0, and 0. So the only terms you get left are this, this, and this. Why? Because the angle between I and itself is 0. Cosine of that angle is 1. The angle between I and j is 90. Cosine of that angle is 0. And so on and so forth. So what you find is these are gone, and the only thing that's left is these diagonal terms, the way he's done it there, kind of diagonal. And hopefully that makes sense. And as you go down one more page, or one more little bit, you'll see that's what he's done. He described it like that. He said, okay, that's what you have here. Now, if you had two vectors, say A, and I've already forgot, so 3I plus 2J I think I had, and I think I had B is equal to 6I. If I want to dot these, what do? I'll multiply those two together plus 0J plus 0K, and these two would be multiplied together, and these two would be multiplied together. So I'd get 18 plus 0 plus 0. So actually this term, which is a scalar, would be 18. And then you would take the length of I, put it right here, the length of B, which is actually 6. You would have that, and you wouldn't have the cosine of the angle. So you just solve for that. It's just that simple. So application. So here he's got, ooh, that's weird. Okay. The angle, so, okay. The angle form two vector intersecting lines. Taylor vector determined from that written as, okay. So here's what he's doing. He's doing exactly that. Dotting these two, say the two we have 18, divided by both lengths, 1 6 and 1, I don't know, 3 squared plus 2 squared, whatever that is, times the length of this other vector, which is 6, which would be sitting right here on the bottom. You take the arc cosine, or your button on the calculator may say that, I don't know. And out of that, you're going to get some angle. And that's going to tell you what the angle is. It's pretty much that simple. If, though, you wanted to find the A projected onto here, you'd end up with that. You can also, and this, okay, so this is kind of, okay, I'm not sure I'm a great artist at this. You can take B back to A or A to B. And what you should find out is, those are pretty much, those are coming out of here. Those are kind of, anyway, I don't want to confuse the issue, so I don't want to say much more. So why would you be interested in this? I'm not sure this is a great example, but there are others probably better. So you've got, let's say you had a structure, and you wanted it to, how should I say, not fall apart. And so what you do is, I mean, I'm not sure that this is exactly what's going on, but let's say there's a turnbuckle here where you've seen those where you tighten them, and then they'll just tension up more and more and more. Essentially, if you wanted to know, okay, so you've got a vector right here, and then say you tighten it up to 1,000 pounds. So that force vector would be equal to 1,000 pounds times UR. It would be going in this direction. But maybe you want to know what component of it's running down that way. Whatever way that is. I mean, this could be drawn out into the field, or it could be perpendicular to that. You don't really know, but you do know you wrote that angle. So you could do this. I want to know the component of that's going along there. Say maybe these bolts are loose, and you're like, oh crap, I got to make sure they're not going to fall. So I'm going to tension this thing into that so that somebody can get on the ladder and the beam won't fall on their head, and they can tighten it up. So what you would do is you'd take F dotted UB, where UB is this thing. And that would tell you the component of F that's running along this way. As you tighten it more and more, it's going to try to pull things over that direction. So you might be interested in doing that. Of course, then you just carry out the math. You'd have that vector, you'd have this vector. And so you multiply that times those two. Well, you'd end up with this. UR dotted with UB. And guess what? If these are both unit vectors, that's pretty convenient, because then it's nothing more. Okay, so look back at the math. UR dotted with UB, B, is nothing more than the unit, the length of that vector, the length of this vector, which these are unit vectors, cosine of the angle. So it'd be 1,000 times the cosine of the angle. Why? Because that's 1, 1. Take this, put it in here. What you're left with is 1,000 times the length vector, cosine of the angle. Well, that and that are both 1. So just like that, you could say, okay, I have this vector, I tighten it down. What's this angle? Take the cosine of it. That's the amount that's being shoved down that edge of the beam. There are other probably better examples. I'm sure they're in the problem sits. So, so you'll find, okay, so here he's talking about what I talked about, a second or two ago. Something you already knew. If you had a vector and you're wanting its component along this side, you take the cosine of the angle. He's saying UA, well, UA is in that direction. So, that's the length from here to here. You take the cosine of that. That's what you learned from trig. Now, what he's doing here, this is kind of weird. When you were in trig, you learned that this length is A, that length of A times the sine of that. Okay. Now he's going to tell you, hey, wait a minute, I'm not sure I know exactly where this is oriented at. But I do know, and he drew this in a weird way, that this vector and this vector are 90 degrees from each other. So that means this A perpendicular, which is what he's saying, the magnitude of it squared plus, and this is what he's going to say in a minute, times this one, which I don't know any other term to use except that A. And think about this for a minute. What is that equal to? So you already know, let's just say this came up as 3, and this came up as 4. 3 squared 9, 4 squared 16, add them together, 25, take the square root, and you get 5, right? Okay, let's take it like that. That means this is 4. I know this. How would you find that? Now, you already know this. So, you already know it's 3. 3, 4, 5. But, if you take 25 minus 16, you get 9, and you have something squared is equal to that, tells you back that it's 3. So what I'm saying is, he may say, without using sine of anything, what's the length of here? Well, if you had this one, and you had that one, move that to the other side and take the square root. So, in other words, the equation would look like this. A perpendicular, the length of it would be the length of the original vector squared. Actually, that's, anyway, I sort of did that weird. Okay. Minus A sub I squared, and take the square root. So this is something that's kind of weird because you're used to just putting sine down. But there may be a case in which this is you're rolling it somewhere and you're not exactly sure how to do it. And he'll present problems to you that it will not be obvious how to do this. But it will be obvious that if this vector, no matter where it's at, and this vector, if they're 90 degrees apart, and I have this length and that length, then I can basically back that one out real quick without ever using any trig. And so I think that's, he just repeated his picture there. Oh, and am I mistaken, or did he repeat his picture again? Okay, that's the same picture as that. Okay. Okay. Okay, I don't know why he repeated the picture 3 times. But anyway. So in other words, I don't know. It just happens. So just making this up. Let's say the magnitude here was just make it easy on myself. This one's this. Magnitude here is 4. But you want to know now the magnitude of that part. Well, that squared minus that squared. Take the square root, and you'll get 5 squared minus 4 squared, and that's the length of that. Or you can work your way around it and start trying to figure out more stuff. Or you could just look at it and just do it that way. Now as you go down, somewhere, okay, I don't know that he actually does that, but okay. So I hope that the dot, there is so much more that you can do with dot products than what I've shown here. That's almost scary if you start thinking in dot products and you get comfortable with them. There are problems that you will be able to solve that no one else will be able to solve. And let me give you a case in point. There, and I don't want to go through the details, but in dynamics, there's a mechanism in which, let's say you had a link, and this is the velocity of one location, and this is the velocity of the other. So it's actually spinning. If you do perpendiculars, you'll find it looks like it's spinning around here. But you need to know the distance from here to here, and you need the distance from here to here. If you can produce base vectors that are not necessarily perpendicular, you can start taking dot products and find this distance really quick, then find this one really quick. Whereas your neighbor is trying to figure out, okay, is this 87 degrees and this is, 72 degrees, and they're busy like trying to figure out all this stuff, and you've already finished your dot product. And so there are cases like that, and there are many, many cases if you start trying to think a little bit like this, it makes things go a lot faster. Now, there was a question about no. Where did it go? Okay, wait a minute. Oh, it's in a new window. It's in that window. Okay. So let's look at this problem. And let me gotta get it on the screen here. Hang on. Okay. So apparently finding the magnitude is not as hard, but the angle is goofy. So I don't know how to get to the angle without going through the magnitude. So I'm going to have to go through the magnitude. I'm sorry. But let's go ahead and do this one and jump, kind of set up here and then go down and try to find these angles. Okay, he just puts the information here. And then he says, determine the magnitude of the resulting force acting on the, okay, I didn't know it had a name. But anyway, on the thing. Okay, so let's list them this way. I'm going to list them all vertically. I'm going to do F1, F2, and then F3. Okay, and the reason I do that is because then I can grab the I's vertically. Here, I and J. I and J. And then I and J. So you can kind of see what I'm going to do. I'll list this, and then I'm going to say the resultant is equal to the sum I and J. So I'm going to add this and this and this to get that. This and this and this to get that. And then I'll be done, except I got to take the magnitude, so I got to take that squared and that squared, take the square root. But I got to figure out F1 first. F1 goes back to the left. Okay, this is where I think I'm projecting it here. Cosine of 30, it's F1, so it's 900 cosine 30, but it's going backwards. So I've got to kind of shoot my equal sign over here. Now, it's also going down. So to me, I look at it like, once I find the 1, I can just repeat it. It's going down. Sine of 30. So again, to me, the angle between here and this is the way I always think. I never think of what's the sine. To me, I think the sine is the place that's filled that is not the cosine. Sounds weird, but that's kind of the way I think about it. Because I only have to remember one thing. You're probably having to think opposite or adjacent over hypotenuse. I'm not thinking of that. I'm thinking of the sunlight hitting this, projecting it through 30. That is cosine 30. That thing was 900, and I'm done. So 2, that didn't have anything going there, but 2 is 500. But it looks to me like it's going down. Now, 3 is 600. So I can just put the 600. It is going to the right. This component's going to the right, and it's 3/5 of that. And it is going down, and it is 4/5 of that. So now, I don't know how I can use photomath to do that. So I'm going to have to just do a calculator. I hate that too. Maybe I'll do it this way. Okay, so I'll take that number, put it right there. You'll find that there's a convenient thing I can do in a second. Maybe. Let's see. It tells me there are probably other digits. I don't even want to see the other digits. So okay, so this time at 900, and I'll take that off, and I'll put a sign, and then I got that, and this will be 4/5, and then I got that, and did it actually get, it actually figured that part out. Okay. Okay. I'm not sure it's gonna, oh, it did. Okay. So of course you do this, and I mean, if you wanted to, you do that squared, and that squared, take the square root. But the question was more along the lines of the angle. So these angles are very weird, and so determine the direction of that, of the result acting measured counterclockwise from the x-axis. So okay, so it's a minus and a minus. I may not have my directions completely. Okay, so I go back this far, and then I go down. Now, I guess I should go back to the other one. Here, let me just go back to the other one to verify something. Okay. Let me see what this comes up with. That's the magnitude. And so I just want to fill this in just as a verification there. And we'll hope that I don't even want to enter more than 1490. Let's see if that, I don't even care what he says about that. Did I enter 1490? Uh-oh. Have y'all ever had that? Server call failed first. Uh-oh. Ooh. Jeez. Okay. Well, I don't know. So there it is. There's the answer. It's 1490. So the server, I guess if you have a problem like that, I guess like go get a cup of coffee and come back maybe, or reboot your computer or something. I don't know what that's about. Okay. So I got that part right. So let me see if I can fix. Oh, the picture's right in the way. Let me go back to the other view. I think I had a clear view with it. Okay. So he wants to know this angle. I don't think I can enter it because the server, whatever it said, was off or something. So there's a couple of things I could do. You could basically do that and add 180 to it. I don't know. So if I do that, I'm going to do something weird. And what I'm going to do, okay, so the magnitude I already found, that's 1490, right? Okay. And the x component is the 419. So if I say the cosine of the theta, which is no, I better use a different term, alpha. So this is alpha, that's theta. Theta goes all the way to there. Is equal to that component, or the 419 over the 1490, or, okay, I gotta make sure I think it's a cosine of 419 or 1490, and let's see what that will come back as if I have entered it correctly. And it says, wow, that's a little bit surprising. 73 degrees? Oh, yeah. Okay, that's, okay. Now, if I add, here we go. No, if I add, oh yeah, let's do this. Let's see what the Photomath thinks of that one. Will it convert? Interesting. That's how it goes back. Okay, so this angle, the theta, which is all of that, is 253.67 degrees. That's weird. Okay. So even though, so it could give me back this in radians or degrees. So what it did is converted that to pi, gave me back radians, and then converted it to degrees. But that's okay. I do not know. I mean, I can try to put it in. Let's try again. 253. Did I enter that right, or did I enter the wrong thing? Oh, I entered 253. Let's see what he says then. Oh, God. Okay, this is one of those ones. Okay. All right. This is one of those ones that you want to beat the computer. 360 minus 253.67. Yeah. And that is going to be, what? 106.33, but it's minus. So I don't like that, but apparently he does not. Okay, so let me go back to the regular view. So he is not given. So if you look at this, I mean, look at the answer. He did not give me the choice of the 253. He should have said, I'll take 106 or I'll take 253. He didn't have, on the other problem we saw, he gave those two choices. On this one, he has not. So if you're faced with this, just turn around and do something like that and put in the other number. Why does this occur, you may ask? Anybody know why? Why can someone type in their solution, get minus 106, somebody else get 253? It has to do with something that's really weird. Arcsine, arccosine, and arctangent. What are the ranges that you can get out of this? This is something to really think about. He's used the arctangent. This is something to really think. Okay, so let's play a game here, because this game may actually be very important for you in the future. It's a stupid game, but this is a part of what calculators do. Okay, push the wrong button. We've got a few minutes. And this is instructive because it applies to everything. And the reason I'm going to MATLAB instead of going somewhere else is because I want you to see this whole thing. Okay. So let's look at the whole thing here. Now, what are the available? Let's answer me this question. What are the available range of numbers that can go in here and here? So if I look at the sine or the cosine on a plot, I go from here, back to here, back up to here, and back down to here, and it all remains within minus 1 and plus 1, right? I just did that backwards. Did you notice that? So if I do something like arcsine of 2, what do you think is going to happen? Any idea? Let's see. A sine, and I want it to come back in degrees. No, I just want to do a sine of 2. Look real close. I don't know if you can see it, but it has an imaginary number attached to it. Okay, the reason it does is because MATLAB is mathematical software. It's going to give you back an imaginary number if there's not a complete real one. So if you want to get rid of the imaginary number, go back and take that. Oops. And what do you get? You get 1.57. Let's turn it into degrees. And what you get is 90 degrees. So an arc sine of degree at 1 will give you 90. What do you think the arc sine degree of 1 will get, minus 1 will get you? And I'll show you why this happens. It gives you minus 90. So no matter what I put in between minus 1 and 1, the arc sine is going to be between, so here, theta equals this. Theta is going to be between minus 90 and 90. Why do you suppose that is? If you look at the plot, okay, boom. Boom. So what's happening is this is the range you're spanning over. If you start getting over into here, what is it, and you put in this value, let's say this value is 0.9 and that one's 0.9. Hey, well, this one will give you that, but that one will give you this one, but it will never give you that. It will never give you anything greater than 90. It will move it back and give you that number. It stays between that and that. What do you think happens for the cosine? Cosine goes 180. So the cosine will be between, and I'll show you why that is in a second. It's going to be between 0 and 180. And I'll show you why. Now let's double verify that. minus 1 and plus 1 gives you 0. Why is that? Well, if you look at cosine, it starts here, do, and then bang, and then it goes to here. So if you get this 0.9, it's going to move it to here. It's going to give you that answer instead of that one. It stays between 0 and 180. No matter what you put in, if you expect to get a minus 45 degrees, you put it in, you're going to get plus 45. Now, what do you think happens for a tangent? First of all, what are the range of values you can have in tangent? Any idea? Let's put in 1,000. Comes up with 89. So let's see. 90. And it should be minus 90. Now remember what tangent looks like. Does anybody know what that looks like? Lots of digits. 90. Go in here and put in lots of negative digits. Minus 90. So if you look at the tangent is a very bizarre plot. It goes like this, and then it goes like this, and then it goes like this. But it is bounded between minus 90 and 90. So when you start using the equation, he stuck in there the tangent. And he did some weird stuff. He is banding himself to be in this range. If you use arc cosine, you are binding yourself to be in that range. To get out of these ranges, you have to use your brain and look at the plot and see what's going on. In this particular case, it is annoying that he did not give you the ability to select both of those. Because one person could use one set and somebody else could use another set. You get two different answers, but both are right. And so it's either that or that. But he has only selected that. That is his error, not yours. Does that make sense? And so when you start doing arc sines and arc tangents and arc cosines, when you do this, you're binding yourself to a range. It seems really strange, but it's really, it is really true. And that's just the way math works. There's nothing more you can do. I mean, if you typed in arc sine, and then you got the answer, okay, how annoying would this be? Here, you do arc sine of, say, 0.707. Well, that's 45, but it's also 45 and 90 is 135, but it's also, I mean, what if you typed it in and you just got a whole string of numbers? Because that's what it should give you. Legally, mathematically, it should give you an infinite set of angles for any arc sine. Does that make sense? That's what it should do. But mathematically, it's going to bind itself between here and here. Cosine is going to bind itself between here and here. The obvious reason why is this. If you look at cosine, for example, what you are actually doing is I am saying I want to pick this number and I want you to get back to theta. So mathematically what it does is it turns this sideways and looks at it as if it's a function. And here's the function. This is a function. That's not. And so it's turning the thing mathematically inside the computer sideways and getting this and treating it as a function so it can get you the answer. Tangent's really easy. You take this thing and turn it sideways. I mean, okay. It's like that. And here's 0. And this is 90. And this is minus 90. So you can put in large negative numbers and large positive numbers. And that's kind of what you're going to get. You're going to get. So Okay, so this is just to let you know when you're starting to do these arc sines and arc cosines, arc tangents, things may come out, and they'll come out as numbers. It is not your fault that the guy did not include the other choice, the 253. He should have included minus 106 and 253, or 254, or whatever it was. He didn't. It's okay. Just remember that if you get that in there and you think you're right, flip the thing over and do the minus part of it and see if you get it then. That's why you have 6, 7, 8 attempts at these. And if you try them to the point where you're exhausted, just let me know. I can go at your attempt and just click reset and give you a new set of attempts at it. But don't just sit there and go, oh, it's 50, it's 51, it's 52, it's 53. No, don't do that. Okay. I'm sorry this is the way, but it should be a little bit more consistent, but hey. So that should have two choices, and it does not.